Hello, everyone. Thank you for joining us today for our live session. I'm going to hand it over to Chris to welcome you, and then we'll get started with questions from our students. Or from our viewers.
Welcome everyone to the online class and our question and answer session. We're trying to get back to a frequency of about every 2 weeks, so I'm looking forward to your questions. The floor is open.
Okay, the first question that we have today is from Sai Kamir, who's on with us live, who asks, can we create a wormhole? But I think we should also talk about what a wormhole is and whether we've ever even seen one.
Right. So wormhole is a concept from gravitational physics that is, it's a speculative idea. And so to put it up front, no, we have never seen a wormhole. We don't know that they actually exist. They are allowed in the theory of relativity, and they are allowed in a particular situation of curved space-time where essentially the place where a black hole is connects to another part of the universe, a very distant part of space-time, where possibly what goes into a black hole may come out at the other side as a wormhole. And so a wormhole is a sort of connection point in space-time between two places that would otherwise be very far separated in space and time. It obviously implies that space-time has significant curvature for that situation to arise. The universe we live in, it turns out, is almost completely flat, spatially flat on large scales. We know this by measuring how radiation from the microwave background has traveled across space and time for 13.8 billion years since the Big Bang. So with pretty high precision, within 1%, space-time is flat or Euclidean in 3 dimensions, which means that the places where gravity is really intense and where a piece of the universe is pinched off from the rest of the universe, as in a black hole, is not obvious that it would connect to another region of space-time far away. So in the universe we live in, it's perhaps implausible that wormholes actually exist. And the fact that they're allowed by relativity doesn't mean that they exist. There's all sorts of things that don't break a law of physics that don't actually happen in our universe.
Sorry. Thank you very much, Chris. The next question is from Ramya, who sent an email, who has a question about distances. I want to know about the distance between celestial objects and how it is calculated or estimated, and how can we predict, or I assume they mean calculate, the size and mass of celestial objects?
Well, it sort of depends on what you mean by celestial objects. If we imagine the more close by celestial objects, which are indeed stars, so the stars in our galaxy, how do we know the distances to the stars and therefore their physical properties? If the stars are close enough, we can actually measure their distance by a direct geometric means, parallax. And that essentially means using the distance the Earth travels in its orbit of the sun to gain 2 different perspectives on a star. And you actually define a long, skinny triangle, just as a surveyor would if they were trying to measure the distance to a tree across a river and they couldn't cross the river, but they observed the tree from 2 different perspectives. So that method of plane geometry used in surveying is also used to measure the distance to nearby stars. And that works out to distances of a couple of 100 light years, which does include thousands and thousands of stars. So for those stars, we measure their distances very directly by geometry. Now beyond that, and in fact satellite, that's from the ground, and satellites, Hipparcos satellite and its successor Gaia, have allowed us to measure parallax distances now to millions of stars. So this has improved quite a lot, and to distances of perhaps 10,000 light years, which is about 1/10 the size of the galaxy. Now beyond that, we have to use more indirect means, which means we have to understand something about the physical nature of a star, whether it's a giant or a dwarf or a supergiant, its age and its stage of evolution, to infer its luminosity, and then its apparent brightness will give its distance, just because of the way light travels through space and diminishes in intensity with the square of the distance. That's a much more indirect method because it relies on the astrophysics of stars, or knowing enough about a distant star to say what kind of star it is and what age it is. So that's less certain. Precision maybe only 10%, 20, 30%. Beyond that, it gets very difficult. Measuring individual stars in distant galaxies and more separated from the Milky Way is only possible if they're extremely luminous stars. and have particular properties that key to their luminosity, like Cepheid variables or Lyrae variables. So measuring the distance to celestial objects is okay within our neighborhood, quite precise. Within a reasonable chunk of the Milky Way, it's still done by geometry and fairly reliable. Across the rest of the Milky Way into nearby galaxies, it starts to get much less certain. And because every other property of a star, its mass, its size, and even its evolutionary stage depend on knowing its distance, all other uncertainties of stellar properties key to distance.
Thank you, Chris. The next question is from Junaid Atta, who is on with us live, who would like to know if there is a connection between dark matter and dark energy.
Cosmologists have wondered whether there might be a connection between dark energy and dark matter because, of course, they're the two enigmatic constituents of the universe. Dark matter is the entity that appears to keep galaxies together or stops them from flying apart. It's also the ingredient of the universe that outweighs normal matter by a factor of 6. So it's the dominant mass ingredient of the universe. And it's also been responsible for slowing down the expansion rate of the universe over cosmic time. So we think dark matter is real. We see a lot of evidence that it exists. And it's exerting gravity but not interacting with electromagnetic or other forces. Dark energy is a much more mysterious entity. All we know about it so far is that it makes the universe expand at an accelerating rate. And so it actually has one property that's in opposition to gravity, acts as sort of negative pressure or anti-gravity, if you want to call it that. Now that alone makes it sound unlikely that dark matter and dark energy are related to each other. The other reason it's unlikely they're related to each other is that dark matter appears to be attributable to a fundamental subatomic particle. We haven't detected that particle yet, but there are experiments that are fairly likely, we hope, to succeed in the next 5 or 6 years. Dark energy, on the other hand, is probably not attributable to a subatomic particle. In fact, we don't know what it is at all. It doesn't seem to vary over time and space across the universe. It pervades space and just provides this backdrop, positive repulsive force to accelerate space-time's expansion. So those attributes of dark energy and dark matter really do seem quite different, and it's unlikely they're related. Now, cosmologists have noticed certain coincidences about the universe, such as the fact that dark energy and dark matter are fairly close in strength at the present era. That only applies once in the history of the universe, though. And so far, there's no one been able to find a direct physical connection between these two.
Our next question is from an email. My name is Pooja, and I am 13 years old. If gravitational force attracts everything towards it, why does the moon and stars, etc., revolve around planets or other stars instead of coming into contact with each other and colliding?
It's a good question. If two objects are drawn together by gravity, they should seem to fall together and combine. And in fact, if two objects were just held apart in space and then you let them go, eventually their gravity would make them fall towards each other and come together or collide or smash together or combine. But in an orbit, you have a different situation. In an orbit, the objects that are orbiting each other were formed from a system that was rotating. And so it had rotational energy. And that rotational energy essentially counteracts the gravitational infall force. And so in an orbit, you have a balance between the gravitational inward force that, say, is making the moon go towards the Earth and the centrifugal motion that's leading the moon to stay in its current orbit, or the Earth in its current orbit of the sun. So in these situations with net rotation, there are actually two forces at play, and one of those forces counteracts the other, and that's why the objects don't fall together.
Thanks, Chris. All right, the next question is from one of our live viewers, Anne, who would like to know, was the deflection of light by the sun measured by Eddington in 1919 considered a gravitational redshift?
The eclipse expedition of 1919, which provided a confirmation of the theory of general relativity just 3 years after it was published, was actually a measurement of gravitational lensing rather than gravitational redshift. Both are predictions of general relativity. But gravitational lensing is the deflection of light by matter, one of the profound and fundamental predictions of general relativity. General relativity also would predict that in passing by the sun, the light from a star that was behind the sun would be very, very slightly redshifted by a very tiny fraction, probably 1 part in a trillion or less. And if the technique had existed to detect that, then that would have been a second measurement of general relativity. But it turns out that that is so subtle an effect that that wasn't detected for another few decades in the lab, and it couldn't have been detected by Eddington's eclipse expedition.
All right. Our next question is also from a live viewer. Jason has a question about one of the exercises from our class, which is to identify galaxy types on Galaxy Zoo. Can you talk about what the different types are, and if you have any hints on improving identification skills, because they're finding it to be difficult?
Right. So the question is related to a citizen science project called Galaxy Zoo. It's one of the original citizen science projects of any kind, and it's definitely the one in astronomy that's had the most traction for over a decade. Citizen scientists have classified literally millions of galaxies from various imaging surveys. So classifying galaxies is tricky, and it's actually still one of the areas where humans do a very good job and machines don't do a perfect job. So citizen scientists doing galaxy classification are not just doing mindless work that a computer could do better. It's not that case at all. Obviously, the big demarcation in galaxies is between what are called early and late type galaxies. Early type galaxies, galaxies with old stellar populations that formed early in the history of the universe, are smooth and elliptical, and so elliptical galaxies are the classic archetypes of those. Late type galaxies are galaxies where the stars have formed late and may continuously be forming, such as in the Milky Way, which is a spiral galaxy. And so spiral galaxies are late type galaxies with beautiful spiral arms, with patchy blue and white hot stars and regions of dust between the stars, with a central peanut-shaped bulge where the stars are older and orange or yellow. So those are very simple demarcations. It's easy to tell an elliptical from a spiral. But then there are regular galaxies of different sizes, and some of these regular galaxies have the hints of spiral arms. So when you get to the later type spirals, the sort of SC and SD spirals in the classification scheme of Hubble, then it starts to overlap with irregular galaxies because they're a little more chaotic and they don't have a beautiful spiral pattern. So this is where classification can get difficult. Also, there's the classification of galaxies called the S0 galaxy, and that's a galaxy where the bulge is extremely large, and they're not the same as ellipticals because they can have some gas and can have some dust. And so distinguishing ellipticals from S0 galaxies is also tricky. And again, experts sometimes don't always agree on this. Another part of classification that can be difficult is the question of whether a galaxy has a bar or not. Turns out the Milky Way does have a bar. This is a horizontal feature emerging linearly from the nucleus of the galaxy, and so therefore looking like a bar, usually quite close into the nucleus. There's a lot of stars in there and a lot of light, and sometimes the bars are small, and so they're easy to miss. And so classification schemes of whether a galaxy has a bar or not, experts don't always agree, machines don't always pick them up, and if the galaxy is far away and the bar is small, you just may not resolve it with your imaging material. So these are all reasons why classification can be difficult, and citizen science have a role to play in this. The final reason, of course, is that galaxies are not always symmetric. Spiral galaxies have a symmetry associated with their rotation, a mirror symmetry. Elliptical galaxies have a large degree of symmetry in 3 dimensions. Irregulars, not so much. But the symmetry of galaxies varies enormously from galaxy to galaxy, and that can make classification interesting.
Thank you very much. Our next question is from an email. Christine would like to know if entropy is a mechanism that governs most of the universe and as such tends to lead to chaos, why is there homeostasis in biological environments?
So entropy is a governing principle of the physical universe on most scales, on large scales and also on small scales as well. And it's associated with the second law of thermodynamics. It's a global tendency for systems to become more disordered over time. So the degree of order will gradually degrade. Another way of putting this is things tending towards a heat death in the universe. That's the way of phrasing it, because heat is a disordered form of energy, photons that are unorganized or chaotic. Homeostasis and biology seem to go against the law of increasing entropy, or the second law of thermodynamics, but that's only for a limited period of time and only on a particular scale. Essentially, biological organisms on all sizes, from creatures, physically large creatures, to microbes themselves or single cells, are taking in energy from the environment. They're taking in energy from the environment. They're creating organization out of that in terms of molecules and metabolisms and the various processes of a cell, but they're also releasing heat energy. And so if you follow the disorder through the entirety of the organism, including what's put out by the organism in a metabolism, as well as what it takes in, then the overall, drawing a big envelope around this situation, the overall entropy or disorder is increasing. So there's less disorder in the organization of the molecules in the living creature itself, but increased disorganization in the fact that the organism respirates or emits heat. And then, of course, in the end, when the organism dies, it does degrade. And so even if the organism is able to beat back entropy in limited amounts and for small scales for a limited period of time, in the end, entropy will increase. I'm ready for the next question.
Sorry, my button on my microphone was not working. The next question is from a live viewer, Hussam, who would like to know how much information is available to mankind about life in space, and what do you think about the existence of aliens and flying dishes?
The amount of information about life in space is still extremely limited, and essentially we know of only one place with life in the universe, and it's the Earth. Astronomers are gradually inching their way towards detecting life beyond Earth, and they're doing it by looking for habitable worlds like the Earth, and we've now found several hundred, actually probably close to 1,000 planets that are within a factor of 2 of the Earth's mass, mostly larger than the Earth. So super-Earths seem to be quite common in exoplanet systems. And some significant fraction of these exoplanets that are nearly Earth size are going to be habitable. The question of detecting life on those is a matter for the future and new instruments, because we don't know how to detect life on worlds that are dozens or hundreds of light years away, but it will probably come over time. Meanwhile, the evidence that life has actually already visited the Earth in terms of UFOs or flying saucers or whatever you want to talk about in that regard, most astronomers do not give credence to. They do not think such reports are believable. They don't think the evidence is solid because it needs to be affirmed independently. So a single eyewitness report or a single photograph or image is not convincing. The only way in science we can corroborate things and move forward with knowledge is when they're subject to peer review, when they're subject to the collective awareness of a set of scientists to corroborate and be skeptical about the information, and no supposed sighting of aliens or UFOs or anything of that category has ever passed that very high bar that we set for detecting life beyond Earth. So I'm in the skeptical camp along with most of my colleagues.
Thank you, Chris. The next question is from a live viewer. Edward Hartman would like to know if it is possible for the Earth to have its orbit around the sun move to be, I don't know, either a more elliptical or a different shape by an outside source or an inside source, and still have human life kept intact. And could that happen anytime in the near future?
Yes, the Earth is in a very slightly elliptical orbit. The Earth's orbit is elliptical by about 4%, and so that does produce a slight difference in the Earth-Sun distance, which does affect climate slightly, but of course is dwarfed by the orbital tilt of 23.5 degrees. That's what causes the seasons and really creates the climactic variations on the Earth over an orbit of the Sun. If the Earth were to interact strongly with a passing object, such as a star or a free-floating planet like a Jupiter that happened to get within the solar system, yes, it could be perturbed in such a way that its orbit remained bound to the sun. In other words, it wasn't ejected and it stayed in a stable orbit, but that orbit had a different configuration. And that indeed could do various things. It might change the eccentricity of the Earth's orbit, make it a much more elliptical orbit, which would be challenging for life on Earth, because it would make the seasonal variations much more extreme. It could also increase the orbital tilt, which also would make the seasons more extreme. It's unlikely it would stabilize the orbital tilt or make it close to zero. That would be fine-tuning that I think is implausible. So almost any interaction with a passing body, a passing large object like a star or a massive planet, would make the Earth less habitable, less hospitable for life, but wouldn't necessarily make it uninhabitable. Now, an extreme interaction with a large object would have the possibility of transmitting enough energy to the Earth in its orbit that it left the system and became unbound from the sun. That would obviously be a big problem. Life on Earth could not survive such an encounter.
The next question is from one of our live viewers. Bhishma would like to know if a planet-sized sun exists, and therefore what is the minimum mass of a star?
So the smallest stars, dwarf stars, are small, but they're much larger than the largest planets. So if you go down the size scale of stars, the transition between a fusion object, an object that is fusing hydrogen into helium, or at the feeble end of the fusion spectrum, just into deuterium, is at just under 8% of the mass of the sun. So when you have a star that's about 12 times less massive than the sun, it stops being a star, and it starts to be a brown dwarf, a different type of object that does have heat and will radiate that heat slowly into space and cool off as a hot gas cloud, but is not hot enough to be a star. That transition temperature is somewhere around 1500 or 1600 Kelvin, so a lot cooler than the sun itself. These stars, these cool stars, if you like, without fusion, are still much bigger than a planet. So there's a gap between the highest mass planet that we've been able to identify and the lowest mass star. So people have tried to fill in that spectrum, and they've found a few objects using infrared telescopes in space, the Spitzer Space Telescope notably. But it does seem there's an actual gap between the most massive planet and the lowest mass star.
All right, the next question is from Mohan Malhotra, who is on with us live, who would like to know, how big is our universe, and are there many universes?
So because of the early, very rapid expansion of our universe, there was a period of time in the first third of its history, 4 or 5 billion years, when every point in space-time was moving away from every other point in space-time faster than the speed of light. That means the size of the visible universe, the edge of the universe we can see with our biggest telescopes, is more than the 13.8 billion light years you'd expect. If the universe is 13.8 billion years old, it's natural or logical to expect that we can see 13.8 billion light years away, because that's how far light can travel in 13.8 billion years. But because the space-time was expanding faster than light, we actually have received radiation from regions that are more distant than that by a factor of about 3. So to work out the exact number, you have to use a physical model for the expansion involving the amount of dark energy and dark matter. And when you do that, the number you get in any direction is about 39 billion light years. So the visible universe is 39 billion light years to the edge in any direction, or across 78 billion light years. It's not to say that's all the physical space, because the universe was expanding faster than light. There are regions of space-time that we've never seen in the 13.8 billion years since the Big Bang. We may one day see them, or maybe not, if the universe accelerates in its expansion, but we do think they exist. So the observable universe is not the same as the physical universe. As for whether there are other universes out there, as I've just said, there's more universe out there than we can see, and so in a sense that's the distinction between the observable and the physical universe. As for whether there are entire other expanding space-times out there, or the multiverse idea, the jury is completely out on that. There's no clear prediction of that multiverse idea that we can test because these separate spacetimes are indeed distinct from our own, and so no information reaches us from those other spacetimes, and therefore there's no way we can know they exist. And so for the moment, we just have to say that that's an idea we can't test.
In a related question, one of our live viewers named Constantine would like to know what was before the Big Bang.
So the Big Bang theory or model is a very good, very accurate description of the universe from a very early hot dense stage. And so we can work backwards in this expanding universe idea towards a time when the universe, by extrapolation, was infinitely hot and infinitely dense at time zero. The theory only talks about what the universe does after this infinite cusp of density and temperature. It doesn't speak to what happened before, or equivalently, what caused the Big Bang. So put simply, although the Big Bang theory is very powerful, it makes some predictions that we've tested, it has a consistent set of observations to support it, it says nothing about what happened before the Big Bang, and it doesn't speak to its own cause. So it's not really the full story of creation.
Okay, the next question is from an email from Uliyemi, who would like to know, or who says, the stars are millions of light years from Earth. Does that mean that the signal that we are analyzing now occurred millions of years ago or more than millions of years ago? What's the current situation of the stars now?
Yes. Light travel time is the fastest thing there is, 300,000 kilometers per second, but that's not infinite. And the distances in space between stars and galaxies is huge. And so it takes light substantial time to reach us from distant stars. Now, we tend to only see stars individually in our own galaxy, which is about 100,000 light years across. So the longest that light will have traveled is about 100,000 years. But we can see, obviously, bright individual stars, especially novae and supernovae, in galaxies that are millions of light years away. And so that light has traveled, therefore, for millions of years. And we are seeing those objects as they were millions of years ago. And to answer the question of what those objects are doing now, we actually can't do that. We are just stuck with getting old light. So distant light is old light. And to know what an object is doing later, you have to wait for that light to reach us. So we're always going to be dealing with a time lag in our observations of distant objects associated with the light travel time from that object. And there's no way around that.
Thank you, Chris. The next question is from a live viewer. Rebecca would like to know if a neutron star can lose mass.
So neutron stars, like white dwarfs and black holes, are sort of tombs of matter. They're collapsed stellar remnants that are held together by their own gravity. So in principle, and in the simplest theories of these objects, they cannot lose mass because they're held tightly together by gravity. They're stars that have no more energy production, so they can't blow up or blow apart or lose mass because of expanding envelopes, as happens to normal middle-aged stars or stars late in their lives that haven't collapsed. So the simple answer is no, these stars can't lose mass. Neutron stars, however, do some interesting things because they're also rotating very rapidly, and they essentially are like a giant atomic nucleus. They can actually have material that shifts due to the enormous stresses associated with their angular momentum and rapid spin. And so we've seen neutron star quakes, that is to say, in the subset of neutron stars where there's radio emission, so pulsars. We've used timing observations to show that the neutron-rich material that forms a pulsar is actually shifting and quaking like an earthquake on terrestrial continents. That isn't losing mass, but it's rearranging its mass essentially due to internal stresses, which is quite exciting to be able to observe.
All right, our next question is again from a live viewer, Ranga Rocks, who would like to know why is it that the universe and our shadows black in color?
Well, the darkness of the universe is really to do with the fact that it's very large and that light from all the stars and galaxies in it hasn't had time to fill the voids of space and make the space glow brightly. And the expansion of the universe has something to do with this too, because light from distant objects is redshifted or reduced in energy, and longer wavelength, lower frequency, lower energy. And so these things combine to say that space, the space between stars and galaxies, is extremely dark. And so absence of light is a common feature of the universe. The universe is filled with radiation, but that radiation is extremely low energy, left over from the Big Bang and stretched by the expansion to microwaves.
Thank you, Chris. Okay, our next question is from, sorry, I have to get to my list, is from one of our live viewers, Richard, who would like to know if you can explain the concept of a multiverse. Is there any evidence for a multiverse, or that another universe other than ours may exist?
The concept of the multiverse comes from the idea that if you trace the Big Bang backwards, you're projecting to a quantum origination of the universe. In other words, there was an incredibly early time when the universe was exceptionally small, hot, and dense, when it was smaller than an atom, and that it was the size of a subatomic particle. And so it's natural, and physicists have known this for a few decades now, to say that the universe could have been a quantum event. And perhaps it was a quantum fluctuation, because we know that energy states at the quantum level can fluctuate randomly. And if that's the case, then it's stepping a little further out on the limb of speculation to say that maybe there were other quantum fluctuations and other energy states, some of which may have expanded into universes that could be visible, or maybe universes that expanded for a brief time and then recollapsed, or some that were stillborn, or some that puffed out to a constant size and never collapsed at all sorts of possibilities. And this is essentially the multiverse. It's saying that there's a potential from the quantum origination of our universe to have quantum origination of other universes with different properties, different initial conditions and different properties throughout their chronologies. There's no test of this idea, and the theory of it is not really a mature theory. It doesn't really make clear predictions. So I would say it's in the realm of speculation, and it's really just tethered to the fact that our universe at one point was a quantum event. And so it's speculation about other quantum events that we can't test at the moment.
Thank you, Chris. Our next question is from Edward, who's on with us live, who asks, in your opinion, is humankind ready for an alien species that is much more advanced than our own to come visit?
It's a good question, and really I would say no. I mean, we're fairly immature as a species. We just have to look around the world and see how much strife and war and bloodshed there is, and the fact that we can't take care of our planet and are trashing it and killing species and causing a great dying of animal and marine species, to know that we're not handling things very well. So as a sort of immature ape-like species that doesn't get on well with itself, let alone with other species, the question of how we would receive an alien species of superior intellect and capability is obviously vexing. It's not clear we would react well. It's not clear we would react positively. It's not clear we'd even understand what they were talking about. I think the most likely situation in this encounter is that an advanced species would be so much advanced compared to us that they might be incomprehensible to us or inscrutable to us, or might not, of course, care about us at all because we're at such a lower level of development and intelligence. So that's what I think is the most likely outcome. But in general, I don't think we're ready for it.
The next question is from Brandon, who's on with us live, who would like to know if you could decide on the next major space mission, no expense spared, what would it be? What would you choose, a robotic mission or other mission to a planet in the next decade?
Well, we're starting to get some ambitions now in the solar system. There is going to be a Europa mission, but it's not going to drill under the ice into the ocean. So if I had, a spare couple of $1 billion floating around, I would design a mission which has been engineering drawings have been created for decades ago, which would land on the European ice pack, try and use radar to estimate a place where the ice pack was thin, relatively thin. Of course, it still could be hundreds of meters thick at the thinnest point. Use a nuclear plant, because the spacecraft will use nuclear power to get into the outer solar system so far from the sun. Use nuclear heat energy to slowly melt through the ice pack, concentrate that energy and melt through the ice pack, and then release a hydrobot or a submersible to actually look for life in what would be the dark sub-ice oceans of Europa. That would be an incredible mission and something we could do. It's actually only a step beyond the orbiter that's planned for about 10 years from now, but it goes sufficiently beyond that that it would be considered risky. It would probably take 20 years to execute and probably about $10 billion.
Okay, the next question is from Bhishma, who's on with us live, who would like to know, what is the maximum temperature that can occur in a supernova explosion?
So the supernova explosion is a spectacular event. What happens is when the last energy source is exhausted in a massive star, iron is the most stable element, so after that no energy can be produced by fusion. Lacking pressure support from fusion, the interior of the star, a number of solar masses worth of material, free falls, gravitationally free falls, and it crashes to the center with extreme compression. The shells that fell in first actually bounce, and they meet the shells that are still falling in, and in that compression, close to the center of the star, at the point of core collapse, where different parts of the compression and shells are falling in at different rates and meeting each other on the way out, that compression leads to instantaneous temperatures of several billion degrees. 6 to 10 billion degrees are the numbers that come up in simulations. So in the moment of a supernova core collapse, temperatures of billions of Kelvin are created, and those are of course hot enough to fuse all the elements through the transuranic radioactive elements. All the elements in the periodic table, to the heaviest ones, can be fused in this situation just for a very short period of time.
The next question is from Bill Riddle, who sent an email. And Bill says, the temperature of the sun's corona is very high, at least 1 million degrees Kelvin, yet it's flanked on one side by the much cooler chromosphere and on the other side by cold outer space. So what's heating up the corona?
That's a good question, and it's a still unanswered question in solar physics. It's been unanswered for 50 or 60 years. Eugene Parker, famous physicist and astrophysicist at the University of Chicago in the early to mid part of the last century, the Parker Solar Probe is named after him. He was the sort of dean of solar physics, and he came up with the dynamo mechanism for why the sun gets its magnetic field, and he probably came the closest of any theorist to explaining why above the hot surface of the sun, but hot being only 5,800 Kelvin, you end up with a corona that's a couple of million degrees Kelvin. It's got something to do with magnetic energy. That's not too hard to say that. People have known that for decades. But the actual mechanism whereby the threaded magnetic fields and energy of what we call the surface of the sun somehow transmits enough energy into a plasma to accelerate that much more diffuse medium of the plasma and the corona to the equivalent of temperatures of a few million Kelvin is still unknown. It's some form of particle acceleration, obviously, but we've never been able to do something like this in the lab, so the astrophysics of it are still a little puzzling.
The next question is also from an email from Pat Carville. As far as I can make out, the effects of gravity are felt at the same way if you're traveling at the speed of light. Why should this be? What's the connection? Is there anything else that travels at the speed of light?
Well, to be correct, of course, we don't know anything that travels at the speed of light other than photons. So photons, by definition, travel at the speed of light. And while they obviously have an equivalent mass by equals mc squared, and photons clearly have momentum, just like particles do, because photons can transmit energy to an object that they hit or fall on, we don't know of any other object that travels at the speed of light, and so we don't really know how the gravity is affected by such a situation. The best we can say is that as we try to accelerate subatomic particles in accelerators like the Large Hadron Collider to very close to the speed of light, their masses increase, where the energy we're putting into their increased speed is not actually increasing their speed very much. They're already very close to the speed of light. It's actually going into increasing their mass energy, and so their inertia, and so their resistance to any change in motion. So these are subatomic particles whose net gravity is small. There's no physical macroscopic object like the size of a human or a spacecraft that could get anywhere near the speed of light. And so we don't actually know how the gravity of macroscopic objects is changed by relativistic motion, because of course we can't do that. It would take more energy than is available in the world to make even something the size of a baseball move at very, very, very close to the speed of light.
Thank you, Chris. The next question is from Gitanjali, who emailed a question. Do all black holes have the same density, or are some more dense than others? And if so, does that mean the more dense ones have a stronger gravitational pull?
So black holes do have different densities, and we're defining density here within the event horizon. So the event horizon, or the Schwarzschild radius, because it was named after that astrophysicist from the 1920s, is the definition of the event horizon, the boundary between things that can get out of the black hole and things that are trapped forever. If you calculate the mean density within the event horizon and you go up in the scale, more massive black holes have lower mean densities than low mass black holes, which is interesting. And you can see that what that means is that at the most massive black hole end of the spectrum of billions of solar masses, the kind in active galaxies and quasars, the density of matter inside the event horizon is actually quite modest. So the most massive black holes in the universe, masses of a few billion times the mass of the sun, the density within the event horizon is about that of the air we're breathing, or water, which is not a very extreme density. However, formally, the object is still a black hole, and of course its net gravity, its total gravity, will reflect all the mass within the event horizon, so billions of times the mass of the sun. So we have this striking situation where, as you go up the spectrum of black holes, the mass or the total gravity of the black hole increases, while the density within the event horizon goes down.
Thank you, Chris. The next one is from Aaron Nizani, who's on with us live, who has an astrobiology question. Is carbon-based life more probable in the universe than something else like silicon or germanium-based?
I think the answer is yes, and that's just because carbon, so the premise of the question is that you could possibly have other modes of coding complexity into molecules and therefore potential life functions from other atoms than carbon. Carbon is unique, however, in the periodic table in its ability to form long, stable chains, essentially infinite chains. The number of possible compounds in organic chemistry is essentially infinite, because you can continue to make the chains longer and add loops and sidebars and branches and so on. So carbon is unique in that capability. Silicon sits in the same position in the periodic table in a different row, and so it also has the ability to form bonds. However, those bonds in a detailed electrochemical sense are not as stable as carbon's bonds. And so overall, silicon does not have the proclivity to make as many different compounds and as many stable complex ingredients as carbon. And any other material, any other basis for life, such as germanium or whatever you want to think of, is also not going to be as good as carbon. So while carbon may not be unique as a basis for life, it is definitely the best ingredient, and it's also one of the most abundant elements in the periodic table and in cosmic chemistry. So if life is going to use anything, it's going to use what's available and abundant, and that's carbon.
Our next question is from a live viewer. Maria would like to know, what are black dwarfs?
A black dwarf is really a reference to a star that is below the fusion limits, so it's not creating energy by fusion. It's just a hot gas ball. And at some point, the gas ball will radiate energy out into space. So the transfer of energy by radiation into the depths and cold of space will gradually cool that gas ball off. And eventually its light will shift to lower energies and longer wavelengths. And so it will go from red through the far infrared spectrum, and to visible viewer, it will become black. So eventually a cool gas cloud is essentially a black object, and that's what a black dwarf means.
All right, the next question is from Rohit, who would like to know how we estimate the amount of dark matter and dark energy in the universe.
So these two most abundant ingredients of the universe are measured in different ways. The measurement of the amount of dark matter in the universe really comes from weighing clusters and large aggregations of matter. So we see the large-scale structure of the universe where galaxies are part of larger concentrations of matter, groups and clusters. And then they also exist on their own. So by weighing galaxies, looking at gravitational lensing, for example, to weigh individual galaxies, and then by looking at the motions of galaxies within clusters and weighing clusters, we can put a pretty good estimate on the amount of dark matter in the universe. We can also do this by looking at the aggregate of all the lensing, all the gravitational lensing that especially occurs on very small scales or very subtle forms of statistical gravitational lensing. Both of these are ways of getting the amount of dark matter in the universe, and they tend to agree with each other that it's about 24% of the components of the universe. Dark energy is a single entity. It doesn't have any structure, it doesn't have any shape or form or concentration in any part of the sky or in any distance from the Earth and the Milky Way. And so it's really just one thing, it's one number. And we measure that in terms of the accelerating expansion of the universe. And so that's measured with supernovae, which we use as standard light bulbs to look out through space and measure how the expansion rate has changed over cosmic time. And those measurements were, of course, what were used to detect dark energy in the first place, and they're also used to show that it represents about 2/3 of the universe, so about a little over twice as much as all the dark matter.
All right, thank you very much. The next question is from Brandon, who's on with us live, who asks, can you see with your naked eye any stars outside the Milky Way, or are all the stars you see on a clear night located inside our galaxy?
Yeah, it's a good question. The answer is they're all inside the galaxy. The stars you can see with the naked eye, a dark sight, you can see roughly 6,000, maybe 7,000 stars. If your eyes are good, you're young and your eyes are good and you're at a very dark site outside the city, you can see 6,000 or 7,000 stars. Most of those stars are within a few hundred light years of the Earth. I think the most distant star you can see is a variable star, and it's about 16,000 light years away. I don't remember its name. And that's because it's very luminous. So because you tend to see more luminous objects to larger distances, even with the naked eye, we do see a number of stars that are not hundreds of light years away, but thousands. And the limit is that number, about 15 or 16,000. That's still only 10% of the width of the full width of the Milky Way. So we cannot see outside the galaxy or individual stars beyond the Milky Way. Now, might be that there was a supernova that goes off at some future time in a nearby galaxy that's bright enough to see by the naked eye, but it hasn't happened within our lifetimes yet.
All right, the next question is from Ilsa, who has a question about relativity and time. So concerning relativity, if a watch is taken out into space, does the mechanism inherently run faster? Does it have to be adjusted to speed up? Like, she's unclear on sort of the physical mechanics behind how relativity works.
Right. So, I mean, a clock, let's just say an old-fashioned watch, a mechanical watch, which has a spring and a mechanism to wind up. A mechanical object will change its behavior somewhat depending on the gravity situation it's in. So a watch, a normal, traditional, old-fashioned watch in deep space, will probably behave slightly differently than a watch on the surface of the Earth. But that's not really responsible for how it keeps time. So, and it's not really measuring the relativistic effect in that sense. When we talk about clocks running slower in strong gravity, we're using a fundamental mechanism of nature to measure time, as opposed to a human-constructed object, whose behavior may change just because of the material it's made of and how it was constructed. And those are atomic clocks, which are essentially based on vibrations of atoms or molecules. And so it's by measuring the way atomic or molecular clocks change their timekeeping with respect to gravity that we know that relativity is correct. And what these experiments have shown, going back to the 1950s and 60s actually, a very subtle effect, is that atomic and molecular clocks run very slightly slower in strong gravity than weaker gravity. So near the Earth's surface as opposed to above the Earth's surface is the way the experiment was actually done.
All right, there's a viewer on with us live named Spacetime with Robert, who has kind of questions about the shape of the universe and wants to know if it's correct to think of the current four-dimensional moment in the universe as a slice of a toroid, or what, like, is there a way to help him understand the shape of the universe?
So you can talk about slices of space-time. That's a reasonable thing to do. That's how gravitational physicists talk about it. They make space-time diagrams. You can't represent 3 dimensions, so you usually collapse 1 dimension and make it a 2-dimensional situation with time as the 3rd axis. And you can present that as a perspective drawing, for example, or model. So the torus version of this, slices in toroidal space-time, would imply that there was some space-time curvature in the situation, or potentially curvature of time, where time ran at different rates at different locations in space. Actually, neither of those things apply in the universe because we don't see curvature in space. The space-time we inhabit is flat as far as we can see. And so these toroidal representations don't appear to apply to the real universe that we live in.
All right, we're at the end of our time. We'll take one last question from Roxy Lyrics, who would like to know if we can find out what our Milky Way galaxy was like before. Was it ever a quasar when it was younger? Has it always been the same?
That's an interesting question of the long prehistory of our Milky Way. So we've pieced together some of this history, this archaeology of our own galaxy, by looking at what are called stellar streams. So with satellites like Gaia in particular, we've seen the residue of the galaxies that plowed into each other to build the Milky Way. So we were almost certain that the Milky Way, as most galaxies in the universe, was built from smaller pieces. And so 10, 12, 13 billion years ago, there were dwarf galaxies that came together, and eventually the Milky Way grew. There probably was 1 or 2 major mergers where medium or fully spiral-sized galaxies combined to make the Milky Way. But in the last few billion years, all we see signs of is the Milky Way eating dwarf galaxies. So we think the galaxy has grown. So we can run the history backward of the Milky Way to say that it was originally smaller than it is now, and that it's grown by bits and pieces of galaxies falling in and growing in. In terms of the nucleus and the black hole, that's an interesting question too. The current nucleus of the Milky Way is dark. The black hole is mostly starved. There's very low gas densities right in the nucleus, even though there's a lot of available gas further out. And that explains why the black hole, the 4 million solar mass black hole in our galaxy, is essentially dark and not a quasar. However, it is possible that in the past it went through feeding cycles, which would have made it quite luminous. And we do see evidence of that. There are bubbles whose age can be traced back millions of years, speculating that when those bubbles were created, the black hole had ingested matter and would have shone much more brightly than it does now. That the Milky Way was never probably a quasar, and that's simply because the black hole in the center is very small. It's 4 million solar masses now, so in the past was even less than that, maybe only hundreds of thousands of solar masses. The objects in the distant universe we see that we call quasars have black hole masses inferred to be hundreds of millions or billions of solar masses. So the Milky Way was never a quasar. Good questions on many topics. I've enjoyed them, and we'll be back with you in a few weeks. Everyone who is in the United States, have a good Thanksgiving holiday, and if you're not in the United States, have a holiday of your own. And thanks to Matthew for helping with the session.
Thank you very much, Chris.